This is episode 1 of Scientific Giants Who Change Our Understanding of the World We Live in. And it begins in a dark room in Cairo 1,000 years ago, with a small hole, a patch of sunlight, and a man under house arrest who decided that the world must be measured before it is believed. The man's name was Abu Ali al-Hasan ibn al-Haytham, known in Latin as Alhazen, and the experiment, as simple as a child's game, became a hinge in the history of seeing. Imagine a windowless room. A beam of light slips through a tiny aperture in the shutter and paints an inverted image of the bustling street onto the opposite wall. With nothing more than a hole, a wall, and patience, the world reveals that it travels into our eyes, not out of them. That light goes in straight lines unless something bends it. That seeing is not the magic emission, but a process in matter and mind. In that dark room, Ibn al-Haytham did more than observe a trick of optics. He staged a confrontation between sensation and explanation, and he proposed a compact with reality. We will not accept the testimony of authority or the convenience of intuition until we test what we think we know against what the world actually does. He had not set out to become the conscience of optics. Born in Basra around the year 965, trained in mathematics and natural philosophy, he was, to use a modern phrase, an applied thinker. He could calculate and he could build. At some point, his ambition took on water in the grandest possible way. He believed the Nile could be tamed by engineering, its destructive floods harnessed for predictability and growth. Called to Cairo under the Fatimid Caliph al-Hakim to make this vision real, he confronted the stubbornness of terrain and the limits of his own plans. The story told by later chroniclers is brutal in its simplicity. Faced with the impossibility of the project and the dangers of disappointing an unpredictable ruler, he feigned madness to save his life and was confined at home instead of punished. Whether every detail of that tale is exact matters less than what we know he did with the time the story creates. He wrote, he calculated, and he experimented. Kitab al-Manadhir, the Book of Optics, emerged from those years. 7 volumes in which light, vision, reflection, refraction, mirrors, lenses, and illusions became subjects for orderly investigation. What had been a tangle of competing Greek theories, some saying that rays emanate from the eyes outward to touch the world, others arguing that images pour into us from without, he sorted by experiment. Do we see because something leaves the eye, like the imagined feelers of a nocturnal animal, or because light enters it? If the first were true, then in darkness our eyes alone should suffice. They do not. If sight were instantaneous, then the sun and the stars would leap to us at once. Yet phenomena at the boundaries of perception, dawn's slow sharpening, twinkling that ceases in still air, suggest constraints. He made a habit of turning perplexity into apparatus. With polished metal mirrors and bowls of water, glass spheres and straight edges, he traced rays, measured angles, and watched how images deform through different media. The reflection law, that the angle of incidence equals the angle of reflection, was not to be taken on faith, but checked and rechecked. Refraction, more elusive, demanded a sequence of trials where light entering water or glass broke its straight-line allegiance and bent in regular ways. He catalogued illusions not as embarrassments, but as guides. The moon's apparent swelling near the horizon, the way a stick seems to kink where it dips into a pond, the mischief of after-images, the ghostly doubling when a polished surface is imperfect. Each anomaly was evidence that seeing is not the raw registration of reality, but an active processing, an interaction between a physical signal and the patterns our minds have learned to expect. Look at his method more than his answers, and you see the deeper invention. He insisted on an ordered inquiry. Pose a question, make a hypothesis. Design a test that can, in principle, render the hypothesis false. Measure what happens, and only then permit yourself a conclusion proportionate to the evidence. He was not content to be a commentator on Aristotle or Ptolemy. He wrote a work with a title that still feels like a manifesto, Doubts Concerning Ptolemy. Doubt, for him, was not a posture, but a tool. He praised those who investigated and attacked what they read until it yielded its real meaning, warning against the seduction of reputation. It is not that he despised authority, but that he understood how easy it is to mistake deference for knowledge. In an age when received wisdom had the weight of civilization behind it, he made room for error as a path to truth. That stance, skeptical yet constructive, became a seed whose germination would feed the European scientific revolutions centuries later. When his work was translated into Latin, De Spectibus, it entered a long conversation, reaching minds that would reshape optics anew. Roger Bacon, who absorbed the experimental spirit; Kepler, who would relocate the image to the retina and bring geometry to the physiology of sight; Descartes, who would try to purify method into methodical doubt of everything but the cogito and the mathematical. But what precisely changed because a scholar in Cairo measured light? Consider the chain. The camera obscura, his dark chamber, did not merely prove a point about straight-line propagation. It trained later investigators and artists to see how images can be formed, inverted, focused. Lenses in spectacles, then in telescopes and microscopes, came into sharper theoretical focus because someone had argued that light is a physical entity with regular behavior. Astronomers could trust what a lens showed because geometry told them how the lens transforms the world. Painters, learning from optical instruments, taught themselves to render perspective and light with new fidelity. The world we inhabit now is full of obedient light. Cameras in our pockets, fiber optic cables threading continents, lasers reading and writing, medical devices peering inside bodies without incision. Each of these technologies required additional theories and engineering feats far beyond Ibn al-Haytham's reach, but each also depends on a principle he helped make non-negotiable. If light is a knowable physical thing, then instruments can be designed to harness it, and knowledge can be scaled from curiosity to craft. And then there is the subtler change, which is less about optics and more about what it means to be persuaded. To listen to him is to realize that even honest eyes are not enough. We see with expectations. We see through the filters of attention and habit. We see what our culture and training allow us to notice. The only way to keep the world from collapsing into confirmation of what we already think is to devise trials where the world can disagree with us. It sounds banal now because we inherit it, but it is the difference between medicine as tradition and medicine as controlled trial, between natural philosophy as commentary and science as experiment. It is what allows a nurse in a military hospital to show with a diagram that sanitation saves more lives than heroism. What allows an epidemiologist to trace an outbreak, not to a curse, but to a pump on a map? What allows a physicist to accept that space itself can curve if measurements insist on it? The scientific revolution did not start in a single room in Cairo, of course. But in that room, a particular style of mind made a promise and kept it. Trust will be earned by measured encounter, not granted by name. His writing is striking for an author of his time because it lives at the boundary of mathematics, physics, and physiology. He wanted to know how the eye actually works, the cornea, the crystalline lens, the aqueous humor, the retina, and he wanted to know how the brain makes sense of what the eye delivers. He argued, against older theories, that the seat of vision is not in the eye alone, but in a processing mind that composes a world from signals. He underlined the role of prior knowledge, of context, and of judgment. The very errors of perception startled him into insight. Why do we misjudge size and distance in fog? Why does bright light leave an afterimage? Why does the sun look larger at the horizon than at zenith? He refused to let illusion be the enemy of reality. Instead, he treated it as an X-ray of the act of seeing. We might say, with our anachronistic vocabulary, that he sensed the cognitive in the optical. The picture of him feigning madness has, over time, made him into a kind of proto-modern hero, the scientist who knows that the court's desires cannot make a river obey, who chooses safety and pretense to save the real work for another day. Whether or not the pageantry of that story is exact, it fits the stubbornness of his method. He understood limits, not only of designs and budgets, but of reason left to admire itself. He set traps for error because he knew how subtle error can be. He trusted instruments because he knew our senses are improvisers, sometimes virtuosos, sometimes liars. In that balance, skepticism disciplined by craft, craft disciplined by measurement, he found a style of inquiry that could be handed on. Ideas are fragile when they are only arguments. They become durable when they come with instructions anyone can use to see the same result. Latin Europe took up those instructions unevenly, and yet they traveled. By the time lenses were ground to bring ships closer and moons into reach, the geometry of rays and the behavior of refraction were part of a shared toolkit. When Kepler described how an image forms on the retina, his diagrams felt like continuations of a conversation begun in Arabic. When Bacon insisted that experiment must correct speculation, he echoed a voice that had already insisted on that alignment. And when Descartes put rules to method, his radical doubt about everything but mathematics walked alongside a more modest, more useful doubt about particular claims that can be adjudicated by contrivance and measurement. The current in which Ibn al-Haytham swam became, centuries later, a river with many tributaries, from Francis Bacon's program to Boyle's pump and Hooke's lenses, to Newton's prisms that spilled white light into its chromatic constituents. The continuity matters. Science is not a series of revolutions without memory. It is a conversation that keeps careful notes. Imagine him again in the dark room. He has a slate, a straight edge, a pinhole that he can widen or shrink, a bowl of water he can tilt, a mirror he can polish to a higher luster. He draws triangles of light, tracks paths through air and glass, notes where images sharpen and where they smear. He is not chasing spectacle. He is looking for invariance. He wants to know what remains the same when conditions change. That impulse, to look past the flourish to the rule, is one reason his work still feels fresh. We live amidst 1,000 claims every day, and the ones that last are those that survive the ordinary cruelty of a good test. He would have recognized the logic behind a randomized clinical trial, the discipline behind a blinded protocol, the humility embedded in publishing a method so that others may fail to reproduce it. He might not have recognized our machines, but he would have recognized the worry behind them. How do we distinguish a pattern from a wish, a signal from noise? There is also the matter of courage, which is not often discussed in histories of optics. It takes courage to write against the canon, to declare that a revered cosmology contains mistakes that matter. It takes courage to put down your conclusions as provisional, to demand that others check your work with their own hands. To doubt productively is a social act. It presumes a community that shares procedures and standards, that agrees to let measurement overrule seniority. In that sense, the Book of Optics is both a treatise and an invitation. It invites others to rebuild what he has built and to correct what he has misbuilt. The culture that grows from such invitations is what we now recognize as scientific culture, with its journals and instruments, its seminars and arguments, its method sections and its admissions of error. That culture did not leap fully formed from any single head, but this Basran scholar's insistence on method is a pillar in its architecture. If you want to see his legacy with your hands, you can. Take your phone into a dark room at noon and punch a pinhole into a sheet of aluminum foil. Hold it over the camera lens and point it toward a bright window. The sensor will register an image that you can watch in real time as you move the hole closer and farther. Blur tightening into focus, brightness dancing with aperture, the inverted room resolving itself as an orderly projection. A millennium fades, and you are playing with the same constraints he did, the same compromises between light and precision. Or hold a glass of water over a page of print and notice how the letters bulge and then swim out of proportion as you tilt. The path a ray of light will take is indifferent to your expectations. It obeys regularities that a patient mind can write down. From that obedience, we have made a civilization of lenses and detectors. From that patience, we have made a civilization of methods. Ibn al-Haytham did not end the story he started. Kepler moved the image into the eye with new clarity. Descartes rephrased optics in mechanical terms. Huygens saw wave behavior in light. Newton split white into colors and made chromatic aberration a design problem that would haunt lens makers for decades. Fresnel brought interference out of thought and into labs. Maxwell gave light its equations. Einstein bent it with gravity. But it matters who lit the lamp and insisted we look at what it shows, even when it humbles our intuitions. In a list of giants, He stands because he changed the rules for how we come to know, not just what we claim to know. So we begin the series here, in the dark, with a patient experimenter asking light to disclose itself. From this point, we will move outward to the mathematicians who calculated the heavens without touching them, to the observers who put brass to the eye and watched the moons of Jupiter settle an argument about what can and cannot be seen, to the architects of fields and quanta who allowed the invisible to become calculable, to the biologists who replaced kinds with populations and essences with histories, to the thinkers who discovered that information itself has a physics. Each of them will ask the world a different question. Each will accept a different kind of answer. But the compact they honor is the one Ibn al-Haytham made tangible. No matter how brilliant your idea, it must survive the ordinary cruelty of a good experiment.